All right, so last class we left off at percent ionization. So percent ionization, what you can do is you can solve the ice chart, the ice table for your weak acid ionization, and then you can use the concentration of the ionized acid, being the A minus, divided by your initial concentration of the acid, or whatever, the A minus or the H plus, which the H3O plus would be, most of the time would be the same concentration, divided by your initial concentration of acid, and that would lead you to the percent ionization. It's just another component or another statistic of your acid that you can get. And it's based on initial concentration. So what we can say is that with the increased concentration, it actually decreases the percent ionization. And that's because you're going to have more acid. And in a weak acid, remember, you're having very little of it being ionized. So at an increased concentration, only a small amount in comparison to if you had a smaller concentration would be ionized. So for this one, which weak acid solution has the greatest percent of ionization? It would be the one with the lowest concentration. So that's going to be C, because lowest concentrations have high ionization, high percent ionization compared to higher concentrations. Here you have 10-fold more molecules. So you can imagine maybe in these solutions, probably around the same amount, maybe a couple more molecules in solution A will be ionized, but in solution C, it might be a little couple less, but it's 10-fold less concentration. So the percent of the ionization would be more. So C would be your answer there. All right, so now let's go on to the next two topics. We're going to talk about mixing acids and then bases. And bases, they work the same way as acids in terms of your Ka and your ionization constant, but instead of Ka, it's going to be Kb. So that's why I'm kind of breeze through that a little bit. Ice charts are the same. Everything's basically the same, just for the basic component. Okay, but before that, let's talk about the mixture of acids. Now, if you mix a strong acid and a weak acid, what you're going to have, let's say you have 100 HCl molecules, and they become H plus and Cl minus. And then you have some H2, I don't know, CO3, carbonic acid, fine. Minus, and then some H plus. And this is going to be very little. So in terms of molecules, let's say you had 100 of these and 100 of these. You end up with 100 of these because HCl is a strong acid. And then you end up with 100 of these. So a complete dissociation, as we know. For a weak acid like carbonic acid, you might end up with, and then at the end of the day, you'll have 0 of these. You might end up with 99 of these, 1 of these, and 1 of these. So the point is, if you are trying to calculate the pH of a strong acid mixture with a weak acid, is the weak acid really important? You're going to have the total amount. Remember, the pH equals the negative log of the H plus concentration, or the H3O plus concentration, which is the same thing as H plus. If that's the case, then is this one really going to be that much of a factor in the entire concentration of hydrogen? No. So the dissociation, or the very, very weak dissociation of the weak acid in comparison to the strong acid, is going to be negligible in all cases. So don't really worry about that. Don't really worry about doing an ice chart for the dissociation of the weak acid if you're given a scenario where you have both a strong and a weak acid. You could just use the concentration of H plus in the full dissociation of the strong acid and use that to solve for your pH. Any questions on that? No? Okay. But then let's make it different. If you have two weak acids, then you can do one of two things, which I don't like this first one, is you can generally consider only the stronger one for the same reason. That's based on your Ka value. So if you have a Ka that is very small, let's say 10 to the negative 10th, that's a very weak acid. But if you have a Ka of 10 to the negative third, that's very strong in comparison to 10 to the negative 10. In that case, yeah, the weaker acid we can completely ignore. It's so negligible. Its dissociation is negligible. It wouldn't change the calculations. But if you have one that's 10 to the negative 3 and 10 to the negative 4, that's going to be close enough. So you could be thinking, all right, how close is close enough for the Kas to where I have to consider both of them? I would say, unless it's really, really far off, like 10 to negative 10 and 10 to negative 3, or at least 100-fold off, I would always do the ice charts for the mixture. And the way to actually figure out the pH of a mixture of two weak acids is to do the ice chart for each acid. And you will be given enough information to solve for, remember, H3O plus. That's what we needed to solve for at equilibrium in order to find the pH. So you can do this for acid number 1, and you can do this for acid number 2, giving their conditions. And then you can just add up the H3O pluses from each acid dissociation in order to get the pH. And then you take the negative log of that. So that's how you do the pH for 2 or more mixtures of or weak acids in a mixture. All right, conceptual question. So which solution is more acidic? Now this should be going back to what's a strong acid, what's a strong base, what's going on here. So what do we think? We have a HCl, we have an HF, and we have a solution that's HCl and HClO. And Christina, yep, the answer is A. And the answer is A because it's the only thing here that's a strong acid. Remember, Hickel, Hibber, High, Hino, Hiclo, Hiso. So Hickel is a strong acid. You're going to have 100% dissociation. So you have 1 molar of hydrogen plus. As opposed to 2.0 molar HF, which is a weak acid. Then you have a mixture of 2 weak acids over here. So the strong acid would definitely be a lot higher pH or a lot lower pH, a lot more acidic. All right, now strong bases. So bases are the opposite of acids, right? Where the acids we use H plus dissociation as a way of measuring the acidity. For bases, we use OH minus as a way for determining its basidity. So we know that bases, they like to accept hydrogen and they want to get rid of their OHs. The strong bases, there's no Hickel, Hibber, High for strong bases, but what we want to know is that they're group 1A/2A hydroxides. That's the easiest way to remember it. Things like NaOH, KOH, and a lot of them, some of them are not that soluble. Like magnesium hydroxide is not the most soluble thing in the world, but it's still considered to be a strong, or on the, it's not as strong as NaOH or KOH, but it's on the spectrum of strength. Lithium hydroxide is another one that's pretty strong. So most of them are going to be the group 1A or 2A hydroxides. So what we have here is that when they dissociate, you're going to have more OHs that are in the water. And if you remember, so all the pH it is a battle. It is a tug of war in an aqueous solution between H3O plus and OH minus. It's a tug of war. So whichever side the water is on more, it's going to go towards that way. So if you release or if you dissolve NaOH into water, you're going to have more OH minus ions. That puts the equilibrium, or that puts the solution balance, if you will, towards the OH minus side, making it basic. If you put an acid in the water, the H plus associates and you have more acidic. That's generally how we're going to be viewing this. And then you can, from that OH minus concentration, you can take the negative log of it. So negative log of the OH concentration gives you the POH. Now the POH, very similar to pH. We did talk about it in last class, where the pH plus the POH is going to equal 14. And this means that the POH works on the opposite scale. So if a pH was low, that means, let's say a pH is 1 and it's acidic. So pH is 1. What would the POH have to be? What do you guys think? What would it be? 13. Good. So that's a pretty easy one, right? If only that was a question on the exam. So if you had 13, that means, and so as a POH, that means it's going to be very basic, but it's POH now. Normally this pH would mean basic, so it's the opposite. It would mean very acidic. So POH, literally the opposite of pH. but for bases. All right, then we could talk about weak bases. So weak bases are basically everything that's not considered in group 1A or 2A hydroxides. And they follow the same rules as strong acids, or sorry, as weak acids in terms of dissociation, meaning much less than 1% ionized in water. And the OH, that all that means is the OH concentration that's going to be released into the water is much less than the original weak base. So ammonia is a very common weak base that once you put it into water, some of the only a very small amount of the hydrogen molecules from the water will actually bind to NH3, because what a base is, remember, a base is a hydrogen acceptor. So hydrogen acceptor means it doesn't want to be basic, it wants to gain the hydrogen, whereas an acid wants to lose the hydrogen. So since it's an acceptor, but it's a weak acceptor, since it's a weak base, only a small amount of particles, in this case, just these two, are going to gain the hydrogen and become ammonium, which you guys should know about, NH4 plus, one of the polyatomic ions. So that's how dissociation of a weak base works, very similar. And then I'm going to kind of glide through here because we already have seen this phenomenon for acids, is that we have our base ionization constant known as Kb. A larger Kb means a stronger base. And the reason why is because, again, it's the same exact thing as equilibrium constant, where you're having the products over the reactants. So it's going to be product concentration over reactant concentration to the power of their coefficient. So, and not including the water, right? Because that's a pure liquid. So it's the same exact thing. And here's some common weak bases. And you can see their Kbs are pretty low, right? Because the higher the Kb, the more towards the products you are. Anything with a Kb less than 1 really is going to be considered to be a weak acid. And some of them are very weak. So here you have structure. So amines. So an amine is anything with an NH2 group or an NH3 group. So NH2, you see that in an organic structure. It's called an amine. And here are a bunch of different types. Or you can have them that are in rings that are bound to carbons. But this is more in the organic chemistry lecture. And anytime you have an amine, it's considered to be a weak base or a basic component of whatever structure you're talking about, because it's very electron rich. It has these 2 lone pair electrons, unlike carbon, because carbon is usually bound to 4 different things and it doesn't have any lone pairs. These nitrogen lone pairs in the amine like to take hydrogen. So they see hydrogens floating, H3O plus. It can strip one of the hydrogens off and take it and act as a base. This is why it acts as a base, because it has the electron-rich area and it can take in a hydrogen. And what's the best base? The best base is OH minus. The reason why OH minus is such a good base is because if you look at the Lewis structure, here we go. So if you look at the structure of OH, the Lewis structure, so you have a lot of electrons, right? So in this case, you have a lot of electrons and you have a negative charge. So what happens? Anything that's an H plus, regardless of the charge, you have a lot of electrons, and these electrons want to draw in the hydrogen, so they automatically form that water. So the same approach. Okay, so how do you find the OH concentration, the pH, the pOH of weak bases? Short answer, you do the same damn thing as you did for weak acids. So you do an ice table, but this time you're solving for the OH concentration. Once you have the OH concentration, that's written right here, you can go from OH to POH to pH. So you do the negative log. It may just be one or two more steps. You do negative log of OH concentration gives you POH. 14 minus POH equals pH. And then you can do pH to the negative, or 10 to negative pH to figure out the H3O plus concentration. So from this, you can find out everything. And Henderson, good, Sumi, nice. So Henderson Hasselbeck, we're not going to see right now. We will see it later on. And Luke, yes. Okay, so basically you do the same thing. We're not going to do any examples right now, but on other videos, we will cover a lot of examples on bases and acids from the part 2, chapter 17 homework. And I'll post a lot of content on that. All right, so another thing that's important are the acid and base properties of ions and salts. So last semester, we learned about salts, and we learned that they were just neutral. But this is not true. Salts can either act as a weak acid or a weak base, depending on their ionic components, depending on their cation, and depending on their anion. And the way to really learn it, instead of just memorizing, because what we're going to have here, I'm going to say a lot of stuff, and there's going to be this chart right here, which tells you about the different cations and anions. It's better to understand it. So here's, and to understand what's going on in the solution. So let's just take, you can read this on your own, but let's just take sodium bicarbonate, right? It's a normal salt. It happens to be basic. The reason why it's basic, because when you split it apart into ions, when it ionizes, meaning, remember we went through the net ionic equation, complete ionic equation, that stuff kind of comes back, but we don't have to do that again. But just the concepts of it. It splits apart into Na plus and HCO3 minus. In water, where you have H, for all intents and purposes, you have H plus and OH minus, what's going to happen? NaOH is going to maybe conform. NaOH, sure. And then you're going to have H2CO3 that will form. Out of these two things, this is very similar to net ionic equation. Out of these two things, which one is going to remain as the compound? You're going to have NaOH that's floating around in water, and you're going to have H2CO3 floating around in water. Which one? Good, Michael. You have the H2CO3. The reason why, anybody want to say why? No? Okay, we're running out of time, so I'll just tell you. So NaOH, we learned about it. It's a strong base. That means as soon as it forms, it's going to fall apart. In other words, it's not going to form at all. Na might go near OH, but they're not going to form, since the second it forms, it is such a strong base that it will dissociate immediately. So that means the amount of OH concentration in the water that's free will remain the same, whereas the amount of H plus concentration will decrease. So remember that balance. We have the balance of H plus and we have the balance of OH minus. OH minus will stay the same. H plus will decrease because that H plus that's free in the water will stick to the HCO3 and it will stay there, since its product, carbonic acid, is a weak acid. So a very small amount of particles, maybe a couple of these, will dissociate, but a lot of them will remain here. So in essence, the HCO3 is quenching or sticking the remaining hydrogen from the water, meaning there are less hydrogens that are free in the water to contribute to pH. If there's less hydrogens and this remains the same and the OH remains the same, that means the pH is going up and it's basic. And that makes sense. Look, we have our sodium bicarbonate, it's basic. And that's why sodium bicarbonate or a lot of different sodium carbonate, things like that are in antacids. They're a good weak base. And then you can have general rules from that. So anions tend to form basic or neutral solutions, whereas cations tend to form acidic or neutral solutions. And we'll talk about that in a second. So let's do another. Let's talk another example. Iron chloride. Yeah. Okay. Iron chloride. Iron chloride. What's going to happen when it goes into water? You're going to have F. Ignore the charges for now. We'll just put Fe3 plus Cl minus. Sure. They go into water. You have H plus, OH minus. What's going to happen? OH minus will stick to F or Fe. Sorry. And then H will bind to Cl. But look at that, HCl. We know what that is, hydrochloric acid. It's not going to really form at all. As soon as it meets each other, the hydrochloric, the H and the Cl, it's going to fall apart. It's going to ionize. So that means the number of H pluses that are free in solution will stay the same. And the number of, since FeOH is going to be a weak base, the number of OHs get quenched and it decreases in the solution. Therefore, this solution is acidic. And that makes sense. Cations tend to form acidic or neutral solutions. So meaning cations that are from, that form weak bases. Okay, so I basically said that already. The stronger the acid, the weaker the conjugate base. That should go without saying. We kind of talked about that last class. Here's a list of different conjugate acid, conjugate base pairs. I'm really trying to finish the next 10 minutes or so. Relationship between Ka and Kb. Now, we did talk about this where we talked about concentration. So if you remember, the concentration of the H3O plus times the concentration of the OH minus is going to equal 10 to the negative 14. That is derived from the Ka times the Kb. So the Ka times the Kb equals the Kw, which is 10 to the negative 14. So this is also equal to Ka times Kb. So that's another thing you can figure out. And that Ka and Kb, it means for the same conjugate pair. So the acid is the Ka and its conjugate base is the Kb, or vice versa. But it has to be for the same compound. You can't get a random Ka and a random Kb and multiply them together and get 10 to the 14. That's not how it works. It has to be for the same conjugate pair. All right, so which anion acts as a weak base? Now, weak base, that means when you put this into water, it's going to go to HCl, and then it's not going to do anything. It's going to break apart immediately. When you have HBr, not going to do anything. It's to break apart immediately. It's a strong acid. HF, hey, that's a weak acid. That's good. This is going to act as a weak base because it is accepting a hydrogen and it's kind of holding on to it. What that's going to do is that's going to decrease the amount of H plus in solution, the free H plus, and the OH minus will stay the same, meaning the solution's pH will go up and it become more basic. Okay, so it's another example. It's another example. So metals, same exact approach. Or I kind of showed you that with the iron, but it's the same approach, same exact thing. So the cation metals are usually going to be weak acids. That's because they like to accept OH and they like to hold on to the OH. As you can see here with aluminum, it holds on to hydroxide. So that means there's less free floating hydroxide in the solution. And there's just some examples. There's the summary chart of basically what I talked about. But again, it's better to know the theory of it. More examples. Ionization of polyprotics. All right. So very quickly, if you have an acid that has multiple protons, meaning like something like H2SO4, what you basically need to do are multiple ice charts. So if you have, let's say, H2SO4, which we know is a strong acid, the first hydrogen will come off immediately. The second hydrogen will be more finicky because now that we have HSO4 minus, this is going to be a weak acid. So then it has its own equilibrium with a Ka. The H2SO4 doesn't even have a Ka, and you don't need to do a ice chart because it's a strong acid. So the way to figure out the pH of this would be the pH of the H3O plus from the first step, from the strong acid dissociation step, plus the H3O plus from the weak acid step. But usually, if you're dissociating more than one proton from a strong acid, just the strong step will be significant. And then the weak step will be very insignificant. So that amount of H plus or H3O plus, we can basically make negligible. And that's what they do here, is that the amount of H2SO4 is going to be basically the same amount of H3O plus because the H3O plus that comes from the second deprotonization is going to be insignificant. So here you can see that where you have, in this case, and sometimes it won't be insignificant because, I mean, in this case it is still, but usually removing the second proton is extremely weaker than removing the first one. So most of the time it'll be insignificant, that second deprotonization, but some cases it might not be. And that's very easy to do. All you do is you solve 2 ice charts and you add up the H3O plus concentrations for each one, and you take the negative log of that to find the pH. So, and here's the rules on how to do that. Very simple. And I will go over some homework problems on the next video that I cover with this. Binary acids, we kind of know how this works. The stronger the bond between the H and the anion, then the weaker the acid, because the H doesn't want to come off then. And then oxyacids. So oxyacids, the only thing we should know is that the number of oxygens, well, we'll just cut to the chase. So the number of oxygens directly corresponds to the strength of the acid. And all that means is, and I'll tell you why, is the more oxygens you have, the stronger the acid. The reason why is because these oxygens have a lot of electrons and they have a lot of lone pairs. Those lone pairs will kind of shift the electrons that are on the oxygen making the bond with the hydrogen. They will shift the electrons away, more towards the center of the structure. What that will do is it will weaken the interaction between the hydrogen and the oxygen. And as we know, weaker interactions between hydrogen and some kind of other component means that the hydrogen can come off easier and it will be a stronger acid. So all of these concepts are basically the same, but it's just a matter of, I think, watching this video and hearing me say it a lot of times, where the weaker the interaction between hydrogen and whatever else it's bound to, the stronger the acid. It can come off very easily. And that makes sense. As you remove oxygen numbers, the acid gets weaker because the interaction between the oxygen and the hydrogen, that covalent bond, becomes a lot stronger because there's more electrons that are located in the oxygen and they're not being pulled away by other oxygens. So here's a question: which of the protons shown in red is more acidic, meaning which one will come off easier? That's the one with the most amount of oxygens, because, and it'll be A, because you have this oxygen, all these electrons will get kind of localized more towards the main structure. That would weaken the interaction between this hydrogen and the oxygen. Therefore, it would come off more easily than the other one. And then the last thing is Lewis acids and Lewis bases. It's just, we kind of talked about the definition of these already, but in Lewis, there's another scientist, came up with this kind of description with Lewis acid base theory, where a Lewis acid is a lone pair acceptor. So as opposed to Bronsted-Lowry that talked about a proton donor, proton acceptor, another way to look at it is a lone pair acceptor and a lone pair donor. So an acid, one second, Christina. So a lone pair acceptor would mean that the hydrogen in this case would be the acid, and it would accept this lone pair and bond to it. And then the NH3 would be a lone pair donor, meaning it will donate this lone pair to the bond of the hydrogen. It's just another way of saying it. And here's the definitions on that. And then here's the pH of rain. To end off with a joke, see New Jersey right there. We are pretty acidic in comparison to the rest of the state and the rest of the country. So the Midwest, they're pretty basic. So if you know anybody from the Midwest, you can tell them they're basic because their rain is pretty basic in comparison to ours. But yeah, I will end with that.